Hey everyone, this is Quinn Morley. I'm the founder of Planet Enterprises and the principal investigator for TitanAir. My co-investigator is Narasimhan Bodetti at Washington State University, and our collaborator is Stephen Collicott at Purdue University. TitanAir is a flying boat mission to Saturn's moon Titan. Now, Titan is basically a planet in its own right. It's larger than the planet Mercury. It has a thick nitrogen atmosphere that's actually denser and heavier than Earth's atmosphere. And one of the interesting things we learned about Titan's atmosphere is that in the upper layers, it interacts with the sunlight, and complex organic material is synthesized that we call tholins. And these are actually sort of building blocks for life. And we may have had material like this form in the early days of Earth before life existed here. And as these tholins drift down through the atmosphere, they actually interact with other organic molecules, and they get larger and more complicated and even form amino acids, we think, in some cases. So we may find weird forms of life there, and that's what we're going to try and find out. The other interesting thing is we want to look at the methane cycle on Titan. It has methane instead of water in the hydrological cycle, and so the whole thing's there. It's got clouds and rain and rivers and lakes, and we want to figure out the mysteries of Titan's methane cycle. And we're going to do all this with capillary action. That's sort of the secret sauce for our project. So on Earth, if you look at any particular raindrop, you're going to find millions of viruses, bacteria, organisms. Just proof of life is just pervasive on Earth, even in something as small as a raindrop. So what we want to do with TitanAir is look for a raindrop on Titan. We want to fly through a cloud, fly through a rainstorm, and drink in that rain, and then try and figure out what's going on, if there's life in there, what the chemistry is happening in the raindrop. And so we want to investigate that native precipitation with those complex organics possibly in it. We want to look at also the lakes and say, are the lakes on Titan habitable? What's that environment like? And we also want to investigate the shoreline materials, like the beach area where the lake meets the land, because on Earth, those are very productive places. So here's our concept art. Obviously, this is very striking, but probably not exactly what we're going to send to Titan. It's probably something more like a flying boat on Earth. Something like this. This is the PBY Catalina, very famous military flying boat from World War II. And so if we take the concept art and the PBY Catalina and we add those together, what do we get? Maybe something like this. This is the sketch for our TitanAir. We call it a Laker, a relocatable lake lander. Here's the 1:50 scale 3D model that's on my desk back here. Now, you might notice this looks kind of like a drone on Earth, like a Predator drone or some sort of military aircraft, except it's designed to also be like a flying boat. And then the wings, though, they're not quite as thin and long. They're kind of more chunky than the Predator drones. And the reason why is because this has to basically fit in a launch vehicle. So we don't have, we can't just have as long of wings as we want. And so the way we're going to do that is by having inflatable wings. And so the wings are really thick for two reasons, actually. One is so we can make this inflatable wing design and have enough sort of girth in those inflatable structures so they don't buckle under the load. And the other is we want to be able to fit our capillary system, which I'll talk about in a minute, in the wing somewhere. And the leading edge, and also sometimes near the trailing edge, there's empty space and structure outside of the main spars that carry the load. Okay, and so how are we going to use that empty space on TitanAir to go find that virus in the raindrop, find that life on Titan? Well, we're going to use cacti and sugar cubes. This process, the sugar cube is going through here where it's sucking the coffee up. This is called imbibition. And this is how the cacti work, okay? So they condense water out of the air onto the spines, and it slowly coalesces and gets the droplets progressively get bigger and bigger. And as they get bigger, they're transported down the stem to the trichome cluster here, which is sort of like cactus hair, and then that gets sucked into the stem of the cactus. That's how it drinks water sort of every morning when the humidity sort of spikes, the dew hits the dew point in the morning. Now what we want to do is have this wing skin, the inside of the front of our wing skin. We want to pull the liquid through the front, like if it's raining and the wing's wet, with imbibition, pull it through. And we want to transport it down one direction of the wing towards where our suction, our science instruments are, with sort of a cactus rod. So for our science instruments, continuous fluid analysis is really our bread and butter for our science pathway here. And it's inspired by ice core melting technology, where On Earth, we'll take an ice core from Antarctica and we'll melt it down gradually in layers and get this continuous data profile of what's in the liquid and the dissolved gases that come out of it, and even the entrapped air bubbles that come out of it. And NASA also uses climate science airplanes to monitor aerosol transport on Earth. And so we kind of want to piggyback on that success and figure out, how can we figure out the aerosols that are in the Titan raindrops using instruments and experience from Earth. And one of the things we found is this instrument called the Particle into Liquid Sampler. And the interesting thing about this is it's actually a continuous sampling instrument that uses its own liquids. They bring in basically dry aerosols and then spray a liquid and sort of make this combination of the aerosols and liquid on a plate, and they do the science on that plate. And so our question is, can we just use the native precipitation and do the similar type of analysis, but with aerosols that are cloud-forming nuclei in those raindrops? So here's an interesting idea. We knew we wanted to do shoreline sampling if we could find a way. And so we came up with this idea of a trifibian vehicle that can float on the water on methane, and it can fly to the beach, and it can drive on land to get to an interesting location. Just so we know that it reduces the chances of this vehicle getting stuck and increases the chances of getting that sample back. And it's such an alien environment. We don't know what the mud on the beach of Titan is going to be like. So we feel like this helps reduce the risk of having an issue with that vehicle. And we'd like to have student design teams actually design this part of the mission. We think that could come up with the most interesting and innovative solution for this trifibian vehicle concept. And samples will be returned into a garage on the larger flying boat, and then we could wash down, with the in situ methane from the lake, we could wash down the vehicle, clean it up, and also remove the sample from it and send that to the continuous analysis suite. Now, the TitanAir kite experiment. I hope you guys are ready to learn something. This is called a picovet. I had no idea what this was before I got into this. It's designed to suspend a heavy camera payload under a kite. And this way, when the kite changes angle, altitude, whatever, because the wind varies, the camera stays level. Now, on the Washington coast, we have this sort of mist and fog all summer long in the morning. So my idea was, how do we piggyback off this situation on the Washington coast? We're already trying to find condensation, rain, fog, whatever, with this capillary system. And so on the 17th of July, I actually didn't go to the ocean. I just did the local beach here in Gig Harbor. I took this thing. This is about 700 millimeters from one GoPro to the other, just for reference there. So I took it to the beach, and I found these two poles sticking up out of the ground. These are perfect to hang my picovet on, so I just hung the carabiners there. I was able to set it up. I load this thing with ice. Either end gets loaded up with water ice. And the idea there is it's going to force the condensation. It didn't work as well as we'd hoped. The first thing we did, though, was do some shoreline sampling, some analog shoreline sampling. And then we sampled the local vegetation. And finally, we got in the air. So this is a view from Kopachuk State Park. And there is a little bit of condensation visible on either end here. It's kind of interesting. This is actually the trailing edge of the cylinder. I sort of mounted it backwards. And this is a key insight for later. I'll touch on this if I remember later. So the results of this was ultimately a failure. It was the first of many failures. The O-ring seals failed, and so I collected water that wasn't from the air. It was just from the ice chambers. Now later testing with misting and fogging devices in a fog chamber showed that our system is failing at that first step, the in-emission step. And so the surface just isn't getting wet enough to transport into the holes. Around 24 prototypes have been made, and most of them have been tested. Some of them just went right in the trash. And when collecting dew instead of rain, comes back to the condensation thing. We think the leading edge is a bad choice. At the leading edge, you get a higher pressure, which causes adiabatic heating, and it's going to make condensation less likely. But on the trailing edge, you're going to get a lower pressure, and you're going to get adiabatic cooling, which makes condensation more likely. So you can see that the holes on the experiment designed for ambition, those were on the trailing edge on accident, and that's the side we saw the condensation on, even though it wasn't in the right place. And so what did we learn? Well, we learned that the system does work when the surface is fully flooded. We did some testing later. If you hit it with a lot of water at once, like for a rainstorm, you can actually look on the video and see individual droplets get sucked into the holes. That's pretty cool. We learned that the difference there, like why the kite one doesn't work versus why the flooding experiment does work, is actually because the surface is more important than we realized. And so there's something going on or we need to address. And we think that one of the things we could look at is dung beetles like in Africa, where they collect water on their back, and the back actually has surface features with hydrophilic and hydrophobic areas of the surface in order to move the water to where they need it to go so they can drink it. Another interesting sort of marine engineering thing here, the hull speed, which for planing, the planing speed of the hull, I should say, which is the speed that the boat can actually get up on plane, is twice our flight cruising speed. And so when we go to take off, we'll just fly out of the liquid. We're not going to go up on plane or anything. We're just going to take off. So we'll be sunk down and we'll just lift off. It's kind of crazy to think about. So thanks, everybody. Here's our contact information. Be sure to check out TitanAir.fyi, and we'll take questions now.